let's take our seats and we'll get this space mission started. All right, good morning, everyone. I'm John Connolly. I'm the director of SSP16. I'd like to welcome you here back to the Technion, to the Cinema Theater, where today you'll see 3 excellent pieces of academic theater. We ask each of our team project groups to take this very technical work that they've done and put together a 60-minute-ish presentation of this very complex subject in an entertaining way. So I think we're going to be in store for a big treat today, and we have 3 excellent teams, and they've chosen on their own the order that they're going to go in. Before we get started, I'd like to introduce our jury that's sitting here in the front row. From Technion, we have Professor Pini Gerfel, who's been our local host and who's been responsible for hosting us here for the last 2 months. Pini, thank you. Also from Technion, we have Professor David Mischner joining us as part of our TP jury. Thank you, David, for coming down. From our ISU academic faculty, we have Professor Rene Laufer. Professor, welcome. From the ISU from the ISU management, we have ISU Vice President Steve Brody. And about to join us from NASA headquarters and from the ISU Board of Trustees, we have Mr. Tom Cremens. So without further ado, I'd like to invite you to join us in the year 2045 for the first of our presentations for our team project on artificial gravity.
Thank you, John. Good morning. I hope you are comfortably seated and excited by what awaits you today. Before I start introducing what we'll be doing, please put all your communication devices in rocket mode because we don't want any sound during the presentation. So now welcome to the 2045 Space Studies program. Congratulations to you all. You have been selected among an enormous amount of candidates that would really love to be in your seats. And it's an honor to be the director of such a program, hosting brilliant space-minded individuals that are to become the future of space. Today, we are heading to Starport 1, the perfect example of a childhood dream that becomes reality. I know you are eager to go there, but let's talk a bit about Starport 1. The journey started in 2016 with an ISU team project, Artificial Gravity, with the SSP16 team. The team project was sponsored by Axiom Space, and the SSP was held in the Technion in Haifa, Israel. Starport 1 is not only an engineering wonder, it's the first permanent presence of human in space. It's also a real gateway to the universe as an orbit test stand for exploring space. It is also a wonderful outreach tool by giving all humankind the possibility to access space. And finally, it opens infinite possibilities for new manufacturing and science projects. The first step of our journey on Starport 1 will start in the capsule where you will be introduced all the design aspects of Starport 1. Then, after docking, we will go to the cupola to enjoy the beautiful view of the Earth from space. Then, we will visit the manufacturing and the science modules to discover how Starport 1 works in the microgravity part. And we'll take the elevators to visit the artificial gravity ring. But first, in order to be part of this journey, to be part of this trip, you should have purchased a ticket. I hope every one of you have his ticket. That will allow you to become a true astronaut.
Actually, there's a little bit more that's required. So, because this launch was procured by a US company, American jurisdiction applies. As a result, current FAA regulations require that we get your informed consent regarding the risks of spaceflight. That includes knowledge that this mission might result in serious bodily injury, death, disability, or total or partial loss of mental and physical functions. So basically that means there's a significant risk that you might die a fiery death. As a result, we would really like you to flip your ticket over and sign that little waiver on the back saying that we have your informed written consent that you agreed to get on this rocket. So have a great trip.
Thank you, Kelsey. So now, just before we start, we have one of the candidates who has been a bit late to submit his forms, and we would like to check if everything is okay with our medical team. So please, Yevgenia, can you come here so we can check everything is okay?
Welcome everyone. I am Alessandro, your flight surgeon. Welcome to your last step before launch. Evgenia, we cannot send you up to the space station until you have gone through a thorough medical evaluation. So these forms are key in making sure you completed all the necessary training. I know, but these questions ensure that the passenger is physically fit for space travel, since we do not have all the same access to medical equipment that we have on Earth. So it is important to make sure that you are in good health. Let's see, I see you've checked no heart problems, no osteoporosis, or recent broken bones.
No. And what about my muscles?
Whoa. Evgenia, I'm sorry, but the Outer Space Treaty prevents weapons in outer space, so I'm going to need you to put those guns away right now.
Loss of muscles, that was years ago, when astronauts used to spend many months in microgravity. They would experience muscle loss and lose around 2 to 3% of bone mass per month. Thankfully, our artificial gravity habitat close to Earth gravity levels provides the necessary countermeasures against bone and muscle loss. Now, you're aware that 85% experience space motion sickness? Don't worry, we have medicine for this that can help, and most people adapt within a few days. I also see you've been checked, that you've been briefed about radiation risk.
Yes.
Although many efforts have been made to protect inhabitants and visitors of the station from radiation, it is important to continuously monitor for radiation exposure. Where is my radiation dosimeter? in the pupil. Thank you. Here is your dosimeter. Please wear it at all times. Congratulations. You've passed all your medical examination, and we spoke earlier about the psychological demands. If you have no other questions, please sign this form. Thank you. We are cleared for flight, and let's go.
Ground control, flight to start port 1, ready to start checklist. Engine instruments, check. Navigation instrument, check. All instruments, useful or not, check. I think we are ready to flight. Door closed, seatbelt fastened, ready for final countdown. 5, 4, 3, 2, 1, ignition.
Okay. How exciting was that launch? Please remain in your seatbelts, as the captain has not turned off the seatbelt sign, and we don't want you to start floating off to the ceiling right now. As you are launching, please take the time to enjoy the beautiful views of the Earth. We are launching this morning from Florida. Okay, as we are launching, we are showing you where we're launching from. This animation actually is slightly faster than real time, but still we're just going at 25,000 kilometers per hour. Starport 1 is 600 kilometers above the Earth and in an inclination of 33 degrees. This inclination is the best for utilizing launches from North America, like the SLS, or launching from Spaceport Florida. But we receive cargo and passengers from India, China, and Kourou. Starport 1 is at 600 kilometers, higher than the old space stations. Now we will tell you why we chose this orbit. As you can see, safety is our main concern. We want you, the passengers and the crew, to be as safe as possible. We have chosen this inclination to be not only above the atmospheric drag, but also beneath the polar regions with the high radiation. We are also traveling a bit under the South Atlantic anomaly, but don't worry, those emitters will show you if you have a problem. In addition, our station is in an area of less space debris. All these massive mega constellations that have been popping up in the last decade is all higher up, from 800 or 1,000 kilometers high. But we are just below them, and still we are protected by active debris removal technologies. And now, as we approach the station, take the time to enjoy the view, and you will meet the architect.
Good morning. I am the architect. I created the Starport 1. Now, undoubtedly you have a lot of questions, but being students, some of my answers you will understand and others you won't. Take a look at that window. Ain't she a beauty? Once we get off this bucket and into the vastly superior Starport 1, you will be able to appreciate that she is a classic rotating ring artificial gravity design. And my station spins at 2.9 rounds per minute. It's pushed by 8 VX200 variable specific impulse magnetoplasma thrusters. And this way I created gravity. People are not adapted to space. So I had to adapt space to them. My station was envisioned as a city with 32 modules, all connected to a universal adapter, connecting them to the ring. The ring carries water, it carries the structural load, it carries the thermal control, it carries the power. And you need a lot of power for 200 people. So we went nuclear. I installed 3 fusion reactors, able to produce 9 megawatts of total power for the entire station.
This whole power source is in full compliance with the UN principles relevant to the use of nuclear power in outer space, which recommend observation of the International Commission on Radiological Protection's objectives.
Thank you. Now I regress. Why are we in space? We can find gravity anywhere on Earth. We are here to escape it when we choose to. So in the center of our station, I put 8 modules, commercial modules for research and production in 0G. Here we design and produce products you can do anywhere else. We produce science you can do anywhere else. And, well, we also have the 8 docking ports, because you see, starport is always also a port. But the real pride here is the shipyard. We produce satellites and starships that are unconstrained by the tyranny of gravity or the violence of a rocket launch. And this enables us to go forth into the universe, because you see the starport is really the gateway to the universe. However, for the souls not so brave as to venture forth onto new planets, we also provide some local experiences. I designed the cupola to provide the same kind of same kind of insight and overview for simple minds such as yourself, as an architect would have. Speaking of simple minds, I think it's time I turn this over to the engineers.
Ha! Typical architect. He'd never get anything done without me. Hello, SSP45. I'm Tom Major, the assembly engineer, and I've taken some time out from my extremely busy but extremely well-paid job to talk to you a little bit about the assembly of the Starport 1. Now, to start with, you may notice how well I'm coping with the microgravity conditions just before we arrive. Don't worry, if you stay here long enough, you will also be able to cope this well with the microgravity. Now, let me take you back 20 years. When we first started Starport 1, nothing in space was mass-produced. So, the first phase of our project involved discussing with our contractors and their subcontractors on improving their manufacturing techniques. Because as you can see by the size of this enormous station, we needed a lot of components, and we needed them all to come at the same time. So after a few years of setting up the production lines, we started production. Firstly, we started producing rockets, because obviously we need those. And then the central despun section, as well as the structural truss. By the 2030s, we'd started launching. We brought together all 8 of the main manufacturing modules that you can see down the spine of the station, and that allowed us to start microgravity manufacturing. We needed to do this as early as possible, because this allowed us to start paying back our many investors. The next phase was to bring up 2 of the spokes. This allowed us to spin up and perform our first spin-up operation, not only to test all the rotating machinery, but also to check that humans can actually survive in an artificial gravity environment. At this point, we had 24 intrepid astronauts, and the spin-up and testing phase was the least fun for them, as they discovered exactly how much vomit the scientists could make them produce in the Coriolis effect. After we despun our first test stage, we moved on to full assembly. And by 2040, we had a fully assembled ring with 12 inflatable modules. This allowed us to have our first 100 inhabitants, which included tourists, as well as crew and manufacturing staff. Over the 5 years prior to today,
we added the final 20 modules, bringing us up to the amazing station that you can see at the moment. But we're also looking to the future. I'm currently doing feasibility studies to add another ring, allowing us to double our capacity and allow twice as many people to experience the same fabulous views as I do in my bedroom every morning. Finally, we're all optimists, so we like to think that Starport 1 will stay in orbit forever. But as an engineer, I'm also a pragmatist, so we have a deorbit plan just in case it doesn't. The first thing we'll do is remove all the radioactive material from the nuclear reactors and send it back to Earth to be disposed of safely. Then we'll perform a disassembly, which will be essentially the reverse of the reassembly. We'll take off the modules one by one. They'll deploy deorbit sails and be brought down to a fiery and yet spectacular end above the Pacific Ocean.
This is, of course, in full compliance with the IADC debris mitigation guidelines, which require that you have an effective and useful disposal plan in order to mitigate risk to third parties below. So basically, we're making sure that flaming space garbage doesn't end up on your mom's garden.
Okay, that's all from me, and now I invite you to appreciate the view as our pilot brings us into dock with Starport 1.
Ground station, flight to Starport 1, approaching the station. Autopilot off, and we're starting the maneuver. Please remain seated. Up and a little bit more on the left. Not too close. Slowly. Slowly. No, not yet. Done. We're done. Welcome on Starport 1.
All right. Welcome to Starport 1. I'm the commander, and I'm here to welcome you to our beautiful station. You're now in the microgravity part, and this is where everyone comes into our beautiful station. Before we begin our tour, I need to go through some fairly boring emergency procedures. So in the event of some emergency, please make your way to the 4 elevator shafts that will take you into the safety of our artificial gravity section. If anything worse were to happen, please make your way either back to your ship or to the escape pods that we have on this section as well. But now, let the tour begin. So if you'll follow me, we'll go into the cupola room. Breathtaking view, isn't it? We couldn't show you this from the artificial gravity section because it spins at 2.9 RPM, and at that speed, most of you will be sick. And honestly, cleaning a cupola isn't cheap. So instead, we've put it here in the microgravity section. It also hosts our manufacturing facilities. We produce fiber optics as well as other products. Our fiber optics of the Z-band type are of the highest quality, which makes them extremely valuable on Earth. We produce about 2% of the world's supply, or about 1,300 kilometers worth a day. We also produce other things such as luxury goods, pharmaceuticals, other proteins. And we also host science facilities to conduct experiments that used to be conducted on the ISS back in the day. That sounds like our debris alarm. We should quickly go into the operations room.
Hey,
Status report.
don't worry, everything is safe. We have a really great solution for managing our debris. So first, on Earth there is a solution where you have a telescope who will check all the major debris, and if a debris is detected, there will be a laser who will target this debris and will change the orbit. We also choose our Starport 1 at 600 kilometers where there is less than others. Afterwards, we have also for debris that are bigger than 10 centimeters, we have a satellite companion in front of Starport 1 on the same orbit, and it will chase all big debris, so no worries, no problems. But we have
It's great to know that we're safe.
And we have also onboard solution, because for debris below 10 centimeter up to 5 millimeter, down to 5 millimeters, we have also an onboard satellite, onboard telescope, who will also check all debris. And if one debris is found, a laser will directly target it and change the orbits. And to finish, for really, really low debris, we have a really, really nice shielding, where it's done with aluminum and tantalum plate, so no worries. We are completely safe.
Thank you very much for those explanations. You can go back to your menial tasks.
Microgravity is weird.
Unfortunately, because of this delay, we won't have the time to visit our manufacturing and science facilities, so we'll just move on straight to the artificial gravity section of the station. I said it's great to know we're safe. Unfortunately, I won't be able to come with you because I'll probably have to deal with the international fallout of having removed a piece of debris. So I'll just leave you with one of our engineers. Please don't let him fill your heads with words. They're a bit technical.
Commander, did you remove another country's debris without consulting me?
Yes.
Oh, gosh. We've talked about this.
Whoa! That's a lot of people. You're those SSP guys, right? I haven't seen you since like 2016, I think. So my name is Øystein, and I've been living and working in this giant hub here for like the last 30 years, and I tend to like think of it as home. Actually, I have my stuff over in the corner here, and I like sleep there, so on. I thought I would show you a couple of the features of the station, right? So we have some bearings and some seals, and like not the aquatic ones, but stuff that prevents us from dying. So down here in the corner, we have a barricade seal which runs along here, and it kind of stops all the stuff from coming out of the bearings and entering the station, because that would be messy and so on. And we have a couple elastomeric seals on the inside here just for emergency. But then the really cool seal is we have a ferrofluid one, which is like 10 rings in sequence, which drops the pressure by 0.1 atmosphere per ring, so we can go like from 1 bar to like 0 and the vacuum of space and that all not so nice stuff, so we can be like cozy and warm in here. And I don't know if you noticed this like 19-meter giant bearing over on this side here. We have like 8 radial and axial pads there, and then along the transfer tube, and then we have 8 of those radial and axial ones over here as well. And they use those to stabilize the station. They work together with the AOCS and the automatic tethering, kind of to make the whole station a bit dynamic, And we use 4 of them at a time, so we have like redundancy, so we can do, a little bit of servicing while we're actually running the station. I guess I'm boring you a bit though, because you're going to the spun part of the station, right? The fun part of the station, and that's you got to go through the elevators, which is kind of like a big pneumatic post tube, right? And be careful about that free fall Coriolis effect, because it can really like mess with you. And it's the elevator itself is like you have footrests and armrests and a passenger compartment and a cargo compartment. And it's really fun to have a ride there, right? So give my regards to the doctor, okay? Thanks.
Hello, SSP 2046. My name is Ed T. Murphy, and I'll be the artificial gravity specialist.
And I'm your nurse, Les Payne.
Okay, so we need our lovely volunteer back on stage. Yes. So, ladies and gentlemen. So, now that you're in the artificial gravity section, would you like to get up and stretch your legs a bit? Oh. Yes, it is. As we've been talking about, the Coriolis force is a real issue with us. As you saw, she tried to get up, and as she was getting up, she was being pushed forward by the Coriolis force. And as she was going forward, she was pushed back down into her seat. So you guys are going to have a fun time here. Also in the station, we don't really advise our guests to be rotating their heads across the plane of rotation too often, which in this case is from side to side, because it causes a phenomenon called a cross-coupled acceleration. And this causes our inhabitants to experience an apparent illusion of rotation that doesn't actually exist. So this may cause them to feel sick, maybe.
That was a bad idea.
Yes, it was. But we expect our inhabitants to get used to this over time. So don't worry, soon you'll be walking around as comfortably as I am.
This is a casual reminder that we are not liable if you willfully and intentionally disobey station orders.
Ladies and gentlemen, this is your space flight attendant speaking. On behalf of the captain and the crew, we would like to welcome you on board of Starport 1 Artificial Gravity Habitation Module. In the very unlikely event where emergency evacuation is required, this spacecraft is equipped with 4 evacuation capsules. The capsules are located on the front, on the rear, and on 2 sides of the spacecraft. Please take a couple of moments to locate the closest capsule to your habitation. In case of fire, please immediately put the oxygen mask on your face and immediately leave the module. Please also read carefully the instructions provided in your boarding folder. Tonight, we will hold a drill to exercise all these procedures. In case of a real emergency event, an alarm will be set and lighting on the walls will lead you to the capsules. Thank you for choosing Starport 1.
All right, so real talk, rules. Before you boarded this station, we had you sign a code of conduct, which contractually agrees that you will obey the rules of the station. So most people are okay with this, but some people, they get aboard the station and they get all dreamy-eyed and all excited about the overview effect, and they're like, oh, this is space, we can do whatever we want. But they're wrong.
But guys, this is amazing. We shouldn't be bound by early views. We should transcend the rules of nations below.
Except that each nation independently controls and has jurisdiction over its independently registered modules.
But just think about this. I can start a new business that couldn't exist on Earth.
Yes, you can, but you also have to obey the tax regimes of your home nation.
Well, yes, but I can do whatever I want. There are no crimes in space.
Actually, there are, and you will go to jail in your home country.
Come on. I'm going to have so much fun this summer.
Legal fun.
Earth rules don't apply here.
They do, and if you break them, you will get sued.
Hello, I'm the Deputy Commander. Welcome to the artificial part of Starport 1. Come on, visitors, don't be shy. Come with me. So now, now we will see one of the modules.
Awesome.
Come with me.
Oh,
Okay.
wow.
Yeah, this is the cafeteria module.
This is great.
It's on the first floor of the crew accommodation module. Each crew accommodation module can hold 20 people living here, and they have this cafeteria to meet and eat all together, because socialization is a really important part in a closed environment like this station.
Great.
So we will move to the next module, please.
Cool.
Okay, so this is your module. This is the tourist accommodation module.
Oh, wow. I like that.
Yeah, it's really beautiful. But you have paid for it, you know.
Great, yeah.
So
18,000 euros, I know.
it can hold 10 tourists, and it has really good facilities to eat and relax. So now we will move to another module. Come with me. This is the garden module. It has 200 square meters of garden, and above it, it has little offices with views of the outer space and the garden.
Yeah, I like that tree. It's very beautiful.
Okay, you will come later.
Yeah,
Let's go to the next. So finally, this is the farming module.
Wow, this is great. I'm going to do this. My mom is going to love it.
And here we have our hydroponic farmer that is going to explain you how we grow food here.
Hello, hello, please. Come in, welcome to my farm. My name is Dr. Greenthumb. Here in the agricultural module, we grow all the station's crops using state-of-the-art farming technologies. We have carrots, cucumbers, tomatoes, bananas, all grown in a soilless medium where nutrient-rich water feeds the root bed. As you can see, the lights around you simulate the spectrum of solar illumination with a few special tweaks to get the maximum yield per watt of energy. The seed bank that we have here is the envy of the local galactic region. All this produce is grown fresh. Here, taste a carrot.
Wow, a space carrot. Oh, it's so crunchy, so fresh. It's delicious.
And you have to touch this cucumber. It's really hard. It's awesome.
Guaranteed to taste better than Earth produce. So, all these crops on the station are very important to the health of the inhabitants. Actually, the agricultural module is a closed-loop system with the environmental control and life support system. These plants reoxygenate the air and scrub the CO2 generated by the humans. Humans.
Yeah, plants are cool.
While on the station, all the food, once harvested, is processed using food printers, leading to a delivery onto your plate with very short delivery times and minimal waste. Yeah, wow indeed. While on the station, every time a crop rolls off our assembly line, a child somewhere smiles. Here, have a leaf as a souvenir. That's the end of
Okay.
our tour.
So we have to move, and we are going to meet the Eclipse engineer that is going to explain you.
Come on over here and let me show you our environmental control and life support system. So on a station like this, you can't just open the window for fresh air. Instead, we make our own with this air revitalization system. See the people of Starport 1. Out to the left go the waste products of daily living.
That's great.
The particles and dust and trace gases have to be removed from the air. And also the solid waste processor creates gases that are added to the stream. They all go to the CO2 removal system. Oxygen is added back in, and out comes clean, fresh air on the right for the inhabitants of Starport 1.
You recycle the air? Are you mad?
It's not just the air. We recycle urine into drinking water as well.
There is something in the water. You know, it's because I need to go to the bathroom. What is it?
It's right over there.
Oh, this is so cool. You know, I love artificial gravity.
Soon we'll have more water thanks to him. Starport 1, the place where yesterday's coffee becomes today's coffee.
Hello. What a lively community on board the space station, huh? Oop. Hello, I am the Chief Culture Officer for Starport 1, and it is a role that, yes, I invented after an inspiring summer at SSP16, where I was in the Humanities Department. Did you know that we featured the first naked bum of an ISU video? I hope all of you will contribute your own unique firsts in your ISU experience, besides being the first SSP in space. Now, before you go onwards with your journey, I'd like to explain a bit about the societal structure of the space station and the ideologies and values that were considered in constructing this. I'd also like you all to consider your own individual roles as envoys for all humankind as you journey onwards into the solar system. The society on board has evolved from the rich and diverse cultures of our beautiful home planet, the original spaceship Earth. I'm proud to say that the spaceport houses individuals from dozens of countries all around this world, bringing together hundreds of unique cultural backgrounds and experiences. In designing the societal structure on board, we had to consider a number of difficult questions. What values should we bring to space? What opportunities and lifestyles should be available on a commercial space station? Now, since this was a commercial endeavor, many of our visitors serve our business needs, and so we'd like to thank our highest paying tourists for keeping this bad boy running. We also consider guests for cultural, educational, and outreach reasons. One of the reasons that we welcome you wonderful space students here today. Not to say you shouldn't use all of your vouchers in our cafeteria. I know you're all very excited to try those scrumptious space veggies demonstrated by Dr. Green Thumb. Now, how was our crew selected? It was based on diverse individual attributes and ability to work well together. Here you can see an overview of how crew dynamics have changed with respect to time. You can see that we are just now starting to see a true space city on board with the introduction of permanent residents and trade workers. The core values that we considered in constructing this space city were the minimization of hierarchy, the fostering of a collaborative and accepting environment, and moving society forward progressively and sustainability from our little outpost in low Earth orbit. So in garnering support for Starport 1 from people, businesses, organizations, governments all around the world, we had to think of compelling societal rationales for why we should have such a space city. We were inspired by the International Space Station, which first showed us how cooperation on large space projects can propel human progress through collaborative technology development and diplomacy. We decided to extend this ISS model of international cooperation and marketed the space station as a place to bring people together and as an outpost to monitor, better appreciate, and protect our home planet. In this, we sought to fully exploit the unifying power of the overview effect, which is the wonderful phenomenon that compels all of us as space travelers to care deeply for humanity and our planet. Let's cut to a live feed of the cupola, which you saw earlier, to take a glimpse of some of the breathtaking views you can see from Starport 1.
Oh, wow. Earth, so fragile, so magical. Look at that. Oh, I'm so inspired today. You know, we've been such a silly species with words, creating boundaries. You know, we are so diverse, so unique, so perfect. I feel so inspired. Wow, look at those lights.
Okay, there's another space tourist high on that overview effect. So I'd like to leave you with this. From the early beginnings of Starport 1, the founding team realized that we played an important role not only as engineers, scientists, researchers, entrepreneurs, we were also society builders. This city in space is a representation of what values our species will preserve and how individuals and communities will evolve in the future. Now, I'm not just saying all of this to convince all of you to join the humanities department, even though it's the best. I think it's very important for all of you to consider and to ask yourselves, what parts of humanities should we bring with us to outer space? Which parts of us are worthy? And so, have a wonderful summer, space travelers, and hope to see you at the next SSP on Mars. Let's bring back our director.
Thank you everyone for your attention. I hope you enjoyed this wonderful visit of Starport 1. Now I will invite you to go back to the ship so we can go to the next destination.
Ground control. Thank you, director. Dear passengers, we are back on our ship for our next trip. I hope you enjoy your stay in Starport 1. And now we start our flight. Ignition. 5, 4, 3, 2, 1. Ignition. Thank you.
Please, member of the TP, can you come on stage with us because you also participated in all that?
All right, thank you guys. Oh. Thank you, Starport 1 team. So the way this works is now we give the jury the opportunity to ask you questions for a while, and then we'll open it up to the rest of the floor. So I'll start off. First of all, I very much enjoyed the presentation. You managed to fit a lot of comedy into conveying a lot of information as well, and I think that will make us all remember what you had to told us a lot longer. I'll also remember a few quotes that will be burned into my brain, like a space carrot, it's so crunchy, or another space tourist, high on the overview effect. But okay, but back down to the engineering. I am interested in hearing more about how people and materials get to and from this station, how many docking ports you have, how many simultaneous visiting vehicles you could accommodate, and basically how the transportation logistics train is operated.
So the space station has 8 docking ports the way it's now, but the central section can be extended to accommodate more. There's a central elevator along the axis of the microgravity section, which takes material to the hub where it's transferred to a spoke elevator, taking things further out to the ring.
Great presentation. I thought the interdisciplinary part was very smooth. You guys were great together. A question on the business and cultural piece. Can you talk a little bit more about the evolution and the capitalization? Because it looked like your commercial crew piece didn't start till pretty late, and the manufacturing started pretty late. So what got it off the ground, and what was you talked a little bit about the relationship with governments and the code of conduct, but it wasn't real clear to me, is that a commercial code of conduct, or how did you take the existing code of conduct and mature it?
So I'm just going to address the business side. So we are planning to start very early with manufacturing. In 2033, we'll begin with the modules, the microgravity section, and that would contain the initial microgravity in research. So that would begin to yield some returns. So we are starting with that, and then 2040 with the tourism. So we did, and one of the reasons why we chose this design in the first place to be so modular is so we can begin to have the returns so early in the construction of the vehicle, even if there's some sort of problem or all of the modules are not complete, we'll still have from the beginning some yield. And in terms of policy, you want to address it?
Well, you mentioned maybe a code of conduct on commercial aspects. I don't know if you are referring to the relations between the operator of the station and the suppliers, for example, on board or on ground. This will be dealt by traditional contractual relationships, and all the provisions should be there, mentioning how to act on board and what are the constraints. So normal legal contracts.
I just wanted to add here on the business side, another reason for having the modularity is it allows if we want to if we see, for example, in the business plan, there's more market for having the micro side of a microgravity construction, we could be able to move in the future some of those modules in the rotating part to the weightless part, or vice versa. So that's another advantage of having the modular design.
Okay. We assume that for such a large venture, international cooperation will be required, with many countries contributing to this. Not only the biggest spacefaring countries, but also new countries, emerging countries with special technologies and special also societal input and scientific input. So as we see it in terms of evolution, we assume that at the beginning, the main funding will come from multiple governments that will have to form some type of governance model, and we offer various models for this. And a little bit through so all these governments will again contribute their know-how and will ask something in return. Sometimes it's political benefit, maybe share for the industry or access to scientists to the space station. And then as the space station matures, there will be more revenue coming from manufacturing and tourists, and the governments can take a step backward.
Yeah, so two questions. One is related to the assembly of this large satellite. Would it be done manually or robotically? How do you plan to build it?
That's not really well defined. There's just an idea of being able to produce things probably robotically with manual help, because you already have people in space, but we don't really know.
I mean, my question refers to the actual assembly. Yeah.
Okay, the space station itself, the modules, will be done before spinning, so it would be done with robotic ships as well as EVAs to connect the final docking ports and cables to allow each model to be able to be separated or isolated in case it needs to be.
The inflatable modules themselves will have a docking port where you don't need an EVA, so the connections, the power and data and more connections will be within the ring of the docking port, but the actual truss supports connections that will need to be EVA connected. So once we're flying up the 40 modules, they'll be very easy to connect, but the main truss will require a bit more effort.
Okay, my second question is more engineering oriented. I'm just curious, how do you plan to stabilize this on 3 axis, if you can refer to this?
Right, so obviously one of the sorry. Okay, so obviously one of the biggest differences between this station and, for example, the ISS is the fact that this is rotating, so it's obviously a gyroscope, so we're going to have a lot of issues with precession. So at the minute we have gimbaled Vasimir thrusters around it, so this is primarily to give translational control as well as rotational. In terms of actually how we're going to provide pitch and yaw, we've thought about placing thrusters on the D-spun section to provide pitch and yaw control. Yeah, that's pretty much it. But it's definitely something that has to be considered further in terms of the precession effects of the station.
Someone else? Yes, thank you. Thank you for a very informative as well as entertaining presentation. I have 2 and perhaps 3, but I'll go through quickly. One in the presentation, as I understood the timeline, there was a comment made about producing rockets. And I would think that given perhaps that was a misstatement, I would expect that the commercial world in 2045 has produced sufficient number of rockets and companies and whatever, and you're just essentially buying a service. So that's my first question. I guess I'll allow you to answer that, and then I'll do my other one.
So I made the point about producing rockets because we're going to need 94 launches within a 10 to 13 year window. So I think even if we ramp up our production, we'll still need to have some discussion about mass producing rockets to get that many launches in that shorter time period.
So you see the rocket production as a part of this consortium,
No, it's not a part, but it's part of the preparation that our rocket suppliers will need time to prepare to supply us that much.
Okay, that's what I was waiting for you to hear, the rocket suppliers. Okay. The second question is, I heard something about deorbiting radioactive material for disposal on Earth. Why in the world would you do that? As opposed to deorbiting it towards the sun, or propelling it towards the sun, or do something else?
In terms of deorbiting it towards the sun, that would be very expensive in terms of fuel because we'd have to accelerate it 24 kilometers per second to get it to go into the sun. So bringing it back down to Earth and disposing of it in a traditional way seemed like the best way of doing it.
Also, according to the laws and guidelines of any object in low Earth orbit, everything needs to be deorbited in 25 years from cease of operations. So we are not allowed to throw our nuclear stuff up, according to the guidelines from 2007.
Yeah, we have to be in a higher orbit to send it up rather than down.
I'm not happy with that answer. I thought the guidelines allow for boosting up into a much longer orbit or doing something else. But I would think between now and 2045, our guidelines would be a bit more humane than to bring back nuclear material. But I accept your answer for now.
There's also the sustainability and ethics thing about keeping debris out of space. We discussed debris, and if we boost it up into another orbit, we're adding to debris rather than reducing it.
Of course, and then that station that's up in that orbit, they could just put it to another, but whatever. The third point was I kept hearing reference to the specific rotation is 2.9 RPM. That seems to be somewhat of a strange, not a round number. Was there justification, or was that a given and a priori given to the project?
Well, 2.9 is basically the number we need in order to get police at our, like, the outside of the modules. So we'll have a gradient, as far as I remember, from 0.8 to 0.7 from the bottom of the modules up to the top. So yeah.
So was it a derived parameter based upon your
yeah.
Yeah.
And also from business side, the large, that means in terms of the radius, the larger we make it, presumably the more cost it would be. We'd like to keep as much as possible the cost down because they're pretty high already.
Thank you for your answers.
Very nice show, nice presentation. I have a few questions. First of all, can you give me some engineering data, like the diameter of the station and the size of the modules?
So the size of the modules would be, I don't remember exactly, they're 2100, or what we used in our calculations was 2100 cubic meters. They're about 17 meters long, I think, 14 meters. Exactly, yeah. And the station itself, the skeleton structure is 150 meters, and it would be about between 170 180 outside dimension with the modules attached, depending on what size of module you actually use. Around 10,000 tons, I think, total weight dry.
Okay, and
just multiply this by 421.5.
Okay, okay, no, and also, what is the rate of decay of the orbit?
Hi, as we move, the rotation is inertially fixed, so the cross-section changes.
Okay.
It goes from 25,000 square meters to 7,000 square meters, but our ballistic coefficient is less than 0.01. So we are at maximum 22 meters per day, which means with the Vasimir thrusters or ISP of 5,000 seconds, we can require fuel for station keeping less than 128 kilograms per year. And in terms of the SRP pressure or other, they were relatively insignificant on the orbit.
So how you maintain the orbit in this rotating?
We have the gimbal thrusters that are non-related to the thrusters who are spinning the station.
Oh, they're on the D-span section?
Yes.
Okay. What is the total power required for the...
For the thrusters?
For everything?
9 megawatts.
9 megawatts. And everything is provided by the nuclear reactor,
The
right?
power is requirement is 6 megawatts with 3 megawatts redundancy, which is the 9 megawatt figure we had earlier.
Okay. Okay. And you have no sun, no solar panels at all?
No, the area required to power the station was inconceivably large.
Okay.
Okay.
Well, okay. Thank you.
Oh, yeah. In the first stage, before we build the ring, when we're manufacturing, we have solar panels for that. But in order to power the whole ring, it was, what was it, 35,000 meters squared of solar panels required.
Wonderful picture. First of all, having watched yesterday, let's say, the evolution of this, congratulations to a very, very excellent show, really. With Walter Peters not being here, I have to take up a little bit on the business side again, and then a science question. So first of all, that needs a tremendous amount of money. Yeah. So having probably not a single person with a very big bank account, so how do you plan to raise the money over time and to fund that station over time? The second question would be, being interested in doing science on your station, what will it take me to put a kilogram of science payload or a person on your station, approximately?
Okay, so I'll answer the first one. So, as you saw in our evolution of the station, we start relatively small. So the first few modules we expect to be funded by by governments or consortium of governments, and as we continue, we can bring in more private companies. But we are aware that it is a very big project, which is why we're starting relatively small. And to talk more.
Thanks. Yeah, we actually had a meeting with Made in Space yesterday as well, specifically to try and get some more financial data in terms of how much we think the sale cost of Z-band optical fibers could be. Okay, I'll slow down a bit. I speak very fast. The current global market in 2011 was around 7.5 billion, and we expect that to grow quite considerably. We're targeting the very high end of the fiber optic market, particularly medical and military applications, where the value per meter is very high. Our terms of how much we can produce, we estimated around 1 to 2% of the global output in terms of volume. And because we're targeting the very high end of the market, the initial business numbers we thought in terms of capture around 40% of the market from a financial perspective. So we view that as a kind of multi-billion-dollar revenue source, which we plan to use as one of the main financial figures to help us raise investment. I think also a combination of government and private funding with potentially an IPO aspect, a little similar to how Earthcast did it as well, was also looked into.
On the science question, so I just bring that, the price of the payload definitely depends on which launcher you select. I think the lowest future cost that I've seen was if we look at the Skylon space plane, they're predicting costs as low as $600 per kilo once they've got it up going. I think that's the best I've seen in terms of the research. What SpaceX now is what $2,700 and the reusable Falcon. So we expect it to go down from there.
I have a quick question here. By year 2045, I would imagine there is other people going to be in that sector as well. So you're going to have some competition. So do you have any plans for upgrades, or how do you stay above and competitive compared to potential people in the same sector there?
Well, quick one from me in the assembly part. We talked about looking ahead past 2060 to adding further rings. We can also make the despun section longer due to the modularity. So we can add more manufacturing capability as well as more population.
And we'll by 2045 we'll be able to measure what's the demand for tourism or manufacturing, or maybe thinking of some other ventures, and that will allow us to basically have the evolution of the station be competitive. So we'll be able to be competitive for the long term by constantly seeing how things are and adapting relatively quickly to the market. So that's, I think, one of our major strengths is the very high modularity.
We also looked ahead a spacecraft manufactory, so we could design satellites that aren't conceivable on Earth because they have to survive launch. So very large diameter dishes or very low mass satellites with very little structure, because in orbit they don't have to survive the up to 7 Gs vibration in the launch period. So.
All right, we have just a few minutes. Maybe we could open up to any questions to people who've had their arms up in the back.
So first of all, thank you for a great presentation. It was really awesome, taught me quite a lot. One thing that I missed is space big data. How are you going to deal with all the communication to Earth, and what are you going to do with the tons amount of bytes? Actually, you talked about mass. I'm talking about how would you ship back and forth 1 gigabyte of data. Now, it is shown in research that a tourist that is high on the view produces around 1.35 gigabyte of data. Now, you have hundreds of those on the space station. How would you handle that? And you didn't address that. Maybe you've done in your report, so that's what I'm asking.
So the communications concept we wanted to use was the it's currently under research at the European Space Agency. It's called EDRS. They have 2 geostationary satellites, 180 degrees apart. And instead of downlinking directly to the ground, the station will have a direct laser link to a geostationary satellite, which has a direct laser link to the ground. I don't think they've calculated how much data they can do by this, but we'll have continuous communications at a high laser data rate.
And exactly, actually, so big data can process all our information that we get from the station. So basically, that's your job.
In terms of the amount of data, we wouldn't necessarily have the tourists be able to send Wi-Fi freely. There might be a paid service. In fact, one of our additional revenues could be as like a movie theater, production in space. So a lot of this would take more data, but also could be as well as a source of revenue. In terms of being able to produce movies and television from the astronauts to be able to do the movies as well. So that might reduce our amount of data and also increase our revenue.
Any question?
Hi, well, you already got your first customer. I'm coming on the spaceport. From the agricultural viewpoint, from the food viewpoint, are you like going to grow all types of crops and vegetables on the spaceport, or are you like only going to grow specific items?
Yes.
Everything?
Yes.
And what methods are you going to use upon that?
The methods in use are highly efficient soilless growth mediums. So things like hydroponics, aeroponics, nutrient film techniques, in general, things that avoid the need for soil.
And in the end, you said that you would be also adding a second ring to increase more tourism. The question is, what sort of engineering obstacles do you see in that, and to add a second ring, and how are you going to address that?
Well, the major challenge of adding a second ring, which is just like kind of an idea we have as a maybe, would be in the bearing itself. It's quite a complex system, and the loads on the bearing itself are really they're a bit hard to calculate. They all depend on perturbations and loads from where you have your weight on the ring and so on. So, but it would definitely be the bearing.
And also, when you, like a big hotel doing a refurbishing, we'll probably shut down, disband the station, do a spin-up test with the second ring before opening the grand new hotel. I guess that would be depending on how much revenue you get towards 2060.
We learned at the lecture that actually the debris travels very fast. It is almost impossible to react. So how do you cope with that?
So in fact, so depending on the solution, but the solution I was showing are already existing. So for the telescope on board with a laser, it's a solution that will be implemented next year on the ISS. So it's done by a Japanese company, JIMO ESO, and they are also, for instance, a company like Airbus are also looking for also checking really small debris. So today, we expect that in 2040, they will have even higher technology when next year there is already on ISS to check this debris issue.
All right, thank you. I think we're at the end of our time. Let's give it up for Starport 1. Good job, guys. Good job. We'll be back at 10:15 to begin talking about Mars.